so let's see. Make sure these things are going. Okay. So, see, today we want to really start talking about probability. And we've already finished sort of all that we're going to say about the cost, volume, profit, CVP. And we did a little bit with the time value of money. So we'll do a little bit more. We'll keep doing time value of money and do a little bit more. But now we want to start probability. So we'll be doing a bit on probability. And, why are we doing probability? Well, probability is really the main tool or the main foundation or the main way that people think about risk and uncertainty. And in business, you never really know what's around the corner. You might expect, you forecast, and your predictions may be, accurate, but a lot of times, there's some uncertainty, there's some unknown. And so probability is a way that people think and compute and deal with risk. And in fact, there's a huge part of the economy which is on insurance, which is all about risk management. Okay? And so we'll start out with some basic concepts with discrete sets in the beginning, and then we'll move later to continuous sets. It's similar, related, but a little bit different. And then maybe next week we want to start to think about distributions. What is a distribution? And we'll look at the binomial distribution, which is just one of many discrete distributions. And then after that, we'll talk about what some people call the Gaussian distribution, some people call the normal distribution, but it's that famous bell-shaped curve, which is a classic example of all probability distributions. And we'll look at it primarily because it's a continuous distribution. And then, later on, we'll start doing some things, saying tip of the iceberg introduction to statistics. And then, of course, there's another course after this, Business Core course, Business 310, that hopefully this whole probability section and a little bit of statistics will start to give you a little bit of a running head start into that class. Okay. So basically, we want to think about some of the basic ideas, or initially want to start thinking about some of the basic ideas. And, the sort of foundation for probability is what's called a random experiment. And when they say when people in probability talk about random experiment, they basically mean just a random event or some process or some result or something that you don't know. And so there's some classic examples. One would be a coin toss, right? So everybody knows what a coin is, everybody knows there's a head, everybody knows there's a tail. And when you flip it, nobody really knows. I suppose if you are really super good at physics, you could calculate, when you flick the edge, like exactly where do you hit the edge, and then how much energy does it have, and where are you going to catch it? So if you catch it a little high, a little low, so in some sense, you could calculate whether it's going to be head or tails. But because of the variation in the flick, the variation in where you catch it, the outcome can be kind of random. Okay, and so also another famous would be die, and two would be dice, six-sided usually. Although there are, a few other flavors of die, usually we deal with the six-sided die. In probability. And when we talk about an event, we talk about some kind of an outcome. So if we're talking about a coin toss, it could be heads, could be an event, tails could be an event, or sometimes you repeat these events, these random experiments. So if you did two tosses of a coin, one event could be heads, and then again, if you did three tosses of a coin, one event could be tails, tails, tails. And so when we talk about events, there are some simple events, or they're simple or elementary events, or it could be compound events. So when we say simple or elementary event, we mean an individual outcome. So if we're talking about two tosses of a coin. One simple event could be that there were first one was a heads and second one was a heads. Another individual or elementary event or simple event could be, well, the first one was heads, second one was tails, or it could also have first one was tails and the second one was heads. So those could be events. Of course, the last one would be tails, tails, right? A compound event, so you notice there's sort of one pair of bracket here, is an event comprised of two or more simple events. And so, you might look at this. So here, this is one event. This is, the braces, say that's another event. Here's another event. So there's three events here. Here there's just one compound event. And, you might say the number of heads greater than one, right? So here, in this one, the heads would be 1, and this one also, the heads would be 1. So this one would be heads first, and then followed by tails. Here would be tails first, followed by heads, and then here there'd be two heads in a row. But this compound event, you could say, the events where the number of heads is 1 or more, possibly, okay? The complete collection or superset, we'll talk about union later, sort of the collection of all events. And so here, if you go back to this original coin toss, one event would be heads, one event would be tails, and so we have this superset, the outer bracket, so it's a set of sets, right? This is an omega, which is the very last letter of the Greek alphabet. Maybe you heard of alpha and omega, so omega watches, maybe, omega, so that's kind of the end of the Greek alphabet, so that's kind of like signifying all of them, beginning to end and everything in between. Sometimes these do S, sample space, and N would be the number of items sometimes. Like, for example, if you're doing a 6-sided die, you might think about S6, right? Or the coin toss could be S2. So sometimes we do omega, sometimes we do S, or some variant of S with subscript or sub something or other. Okay. In addition, sometimes it's useful to think about, nothing, where, if you have a coin toss, well, how many times could you have 3 heads? Well, if you're only tossing 2 coins, that's impossible, right? So you might say, well, in that case, it's a null set or the empty set. So sometimes they call this the empty set, the null set. Notice that it doesn't have brackets or these braces. So it doesn't have these. So this is, when you write that sort of O with a slash through it, that is the empty set. So it is a set. And so it's with empty, nothing there, null set, empty set. Okay, and maybe you've heard of random variables, but we want to start to think about random variables. And what it is, it's a way to assign a numerical value to each event of a random experiment. So, for example, you might say the number of heads, right? So, here you might say the number of heads would be 2. Number of heads would be 1, the number of heads would be 1, and then if you had tails, the number of heads would be 0. So in that case, that way would define a random variable, because based on the elementary events, right, we were able to assign a specific number to that event. Okay, and so we'll say a little bit more about random variables later. And so now let's look at some random experiments, right? So random experiment is some process. Outcome is not known with certainty. So let's look at a coin toss. Okay, and so when we say a coin toss, sometimes we're, why are we looking at tossing coins? Well, really, when we say heads and tails, it's actually similar to a purchase or not purchase, right? So obviously heads or tails, it might be 50-50 chance, right? If it's a fair coin, as long as it is a fair coin. If a consumer purchases or not purchases, those are definitely, they go into the store and they either buy or they don't buy, right? So it's like the outcome is like a head or tail. Obviously, the probability may not be 50-50, right? The probability is something else for whether they purchase, this soda or, that towel or that T-shirt or a pair of sneakers or whatever. The probabilities are not a half, but the outcome is either heads or tails, 1 or 0. People might agree with you or disagree with you. Okay, and so again, it may not be 50-50, but the outcome is either yes or no, agree or disagree. Whether you advertised or did not advertise, that's, a choice that somebody made, and based on whether they advertise, that may affect purchasing. If you did not affect purchasing, it may not affect, does advertising affect purchasing? Otherwise, don't spend the money, right? So you would want to be able to understand, the relationship between if I advertise and not advertise, hopefully on, whether purchased or not purchased. So you can see how these events can be kind of related to each other, right? If we're talking about mortgages, right? So a bank might be interested, is this person that we're going to, give the money to, issue the mortgage to, are they likely to default or not, right? And so there's something called a credit score that's related to that. And so individuals or households with a certain credit score, they may be more likely to be current or more likely to be in default, right? And so that would affect, say, the mortgage interest rate that the bank might give to certain borrowers. And so the bank is interested, what's the probability, I have this huge portfolio of loans or, credit card accounts, how many thousands or 10,000s or maybe even a few million. So what's the probability that some of those are going to go into default, right? Because I want to do some business planning or estimating. Manufacturing defect or no defect, you're trying to catch a plane or go somewhere. What's the probability that the flight will leave on time, or what's the probability that the flight will be delayed, right? And so even though we're going to say talk about coins and Dai and these kind of abstract things for a while, they actually, the principles that you learn are actually easily portable or transportable to, real sort of business situations. Okay. So just to get started, right? Suppose we think about tossing a coin, right? And we want to think about what are the events and what is a sample space for tossing a coin, and what's a possible random variable for this experiment. Okay, so what would you do? What would you say are the events? Tossing a coin, right? Clearly it's what? Yeah, heads or tails, right? So when we want to enumerate list them out, it's not required to have this sort of index, although sometimes it can be helpful. And so sometimes you'll see people assign some kind of a number to it, but sometimes you don't. And so we could say do tails. Usually everybody does heads first, followed by tails, right? And so then you might say, total. You could have heads followed by tails, right? So these would be the individual events, heads or tails, and then the sample space, we might call this S2 sample space. Right, and so we could define a random variable, an RV, sometimes we call them RV, which would be the number of heads. So that's an abbreviation for the number heads. So here the number of heads is 1, and then in the second case, tails, the number of heads is 0. And so this way, or kind of like a function in a certain sense, to every event we have assigned a number, so in fact it is a random variable. Okay? So next, continuing, right, if the random experiment is tossing a coin twice, what are the events and the sample space? And what could be a random variable that you assign on that, right? So again, we may define this number. Sometimes if you deal with data a lot, you might hear people talk about a primary key, or PK. And so what it is it's just, usually it's a number, and it's a way to just uniquely define a particular case or a particular outcome or variable. Okay, so let's talk about the events. And so if we toss a coin twice, right, we might get, I'll just say heads, or we might get heads, tails, we might get tails, heads, or we might get tails, tails. Oh, sorry, tails, tails. And, there's no particular reason to assign 1 to head. I mean, if you assign 4 to this and 1 to this, it doesn't really matter, right? As long as the numbers are not, the assignments are not repeated, and then instead of saying event heads first followed by tails, you could say event 2, or you could say event 4. So instead of saying tails, tails, you could say event 4. But anyway, as long as these are clearly demarcated or specified, it's clear, right? So here we would say the sample space maybe S2, because it's 2 tosses of a coin. It would be, heads, 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 tails, tails followed by heads, and then tails followed by tails. So sometimes, it helps to see it in the, enumerated, the table view. Sometimes, of course, it takes up a lot of space. Here, this is sort of the linear, one-line kind of view, and so they really kind of show you the same information, but it's just more compact this way. Might be a little bit easier to see. I'm doing, heads and, heads, heads, and then these sort of flip, and then I do tails, and then these sort of flip. Okay, and then, we might as well stick with our tried and true random variable, right, the number of heads. So in this case, case 1, there would be 2 heads. In both cases 2 and 3, there would just be 1 head, right? They're just in reverse order. Sometimes the order matters. Like it's important that the first one was heads and then the second one was tails, or the first one was tails versus the second one was heads. Sometimes, like in the case of the number of heads, I don't care. We don't care whether it was first or second or whatever, as long as somewhere in the pair there was 1 heads, we'll count it as 1. Okay, and then clearly this one is 0. So again, all of the events in the sample space have been assigned numbers, so that's a random variable. Yeah? Okay. Okay. So another example would be, say, orders at a restaurant. Suppose that at a restaurant there's a choice of appetizer, soup, say it's beef soup, right, or salad, so you could choose a soup or salad. And then for your entree, there's a beef choice, there's a chicken choice, and there's an eggplant choice. And so, if you were running this business, you might wonder, what items are customers most likely to order, right? Now, why would you want to know that, right? Because you want to have some inventory, right? You want to stock and keep track, right? If everybody, likes beef and not too many chicken or eggplant, then you want to make sure you have more beef, right? And then you can, you don't have to buy so much chicken or have so much eggplant on hand. And so that can help your planning, right? And so clearly you want to know what's the probability that your customers are, what's the probability, how many are you going to have, weekday, weekend kind of a thing. And so all of this, likelihood, probability can affect your planning and how you purchase and make your expenditures. Anyway, so how would you do this, right? And so, step one is to assign some kind of variable or letter to all of the cases, right? Because you have to name them in a concise way in order to, use the symbols and the formalism, the sort of technology or the way of doing things is to, have some kind of a compact notation. So for soup and salad, right, typically like, for example, for the entrees, beef, chicken, and eggplant. Beef, B, C for chicken, E for eggplant. That's kind of easy, right? But soup or salad, they both start with S, right? And then some people also want to reserve S for the sample space, right? Because we're dealing with probability here. And so then, well, you might go to the second letter. And so maybe for salad, we'll call that A, sort of the second letter. If we did soup, we would choose O, but then O could be confused with 0, or almost a null set with a strike through. Is it 0 or null or O, or did they forget to put the slash? Is it the null set, And so that's really not such a good choice. U maybe is unusual, kind of the end of the alphabet maybe, and so maybe we'll choose P. But you could choose U, and then that's soup, oop, maybe, and then with the P it's a focus on the P, soup, right? So for the sake of argument, we'll just say P, and then it's good to have all the letters be unique. Otherwise, you could do S. We could have done 2 letters, say. So maybe we could have done SO for soup, or SP for soup, and SA for salad, or SD for salad. So you have some conventions. Usually people stick with 1 letter, but you could stick with 2 letters, or it could be S1, S2, although that kind of is reminiscent of the sample space, right? So anyway, if you can do 1 letter, that's generally easier, but you could do 2, 3, mix in a number here and there, and as long as you assign some meaning and it's clear to you, then you can just go for it. Okay. So now that we've done step 1, we would like to figure out what's the sample space. But before we actually figure out the sample space, the question is, can we estimate the size of the sample space? Right? Because when you try to enumerate or list out all of the sample space, all the events in the sample space, you want to make sure you have all of them, right? And so how do you know if you have all of them? Well, you could count them. Well, how do you know how many? So if you know how many you're looking for, then if you get that many and they're all different, then you're done, right? But if you don't really know how many, it's you might say, well, I can't do any more, so I'm done. But anyway, could we estimate the size of the sample space? Can we estimate? And if we could, how would we estimate the size of the sample space? Any ideas? Ideas? One way to try to think about it, right, might be to go back, right? So to what we've already done. Here, we're doing 1 experiment, right, and the toss of a coin, and we know it's either heads or tails. So there's 2 possible outcomes, right? So that one was easy, right? Here, we did a coin toss, and then afterwards we did another coin toss, right? And so it was, obviously there's 2, and so here we see that there's 4 possible outcomes, right? And so we might say that you know, the the first random experiment that we did, which is a toss of a coin, had 2 possible outcomes. And then the second one, you know, we repeated the same thing. It had 2 possible outcomes. So if we multiply those together, we got 4, right? And so this would be the total, right? So the first, you know, obviously they're the same. They're both 2 and 2. So multiply those, we get 4. So what if we tried to apply that here? Can we estimate the size of the sample space? How would we do that here? Can we do it? I think we can do it here. So how will we do that here? Right, kind of just like what we did last time. We got these 2 sort of a slot for the first one, a slot for the second one, right? So maybe we would have a slot for the appetizer, and we have a slot for the entree, main dish. So for the appetizer, how many choices are there? 2, right? Soup and salad, thanks. And what about the entree? There's 3, right? There's beef, chicken, and eggplant, right? So that's predicting 6 total. Okay? So let's see. Right, so let's do n. And there are a few ways to do that. So events. You know, the customer ordered a, let's say, a salad and a beef, or a salad and a chicken, a salad and an eggplant, right? Or they ordered a soup and a beef, a soup and a chicken, a soup and an eggplant, right? So we could call that case 1, 2, 3, 4, 5, 6. I think we got all of them, right? So you can see how in the first position for the appetizer, we have the 2 choices, the A followed by B. So that's all of them, right? And then for each A, there are 3 possibilities, right? Beef, chicken, or eggplant. And then for the same thing for the soup, 3 possibilities, beef, chicken, or eggplant. Okay? And so the other way that you might say it would be, so you might say that we're looking at a sample of 2 cross 3. Because the first position there's 2, second position there's 3, and then, you know, you would just do the same thing. A, B, AC. And then the AE pair, followed by the PB pair, the PC pair, and E pair. Okay, so that would be your sample space. Okay, what about a random variable, right? Lots of possibilities, right? Maybe one choice could be vegetarian. Right, and so the soup, right, was actually a beef soup. So anything that had, oh, sorry, this is the salad, right? So here, this is the soup. So it was a beef soup. So anything, you know, with beef is kind of out, right? With the soup is kind of out, right? So here, beef, that's not vegetarian. Chicken, that's not vegetarian, but eggplant, right? So this function or this random variable assigns 0 to almost everything, and it basically assigns 1 to the combinations that would be vegetarian. So it is a random variable. one of the many possible random variables that we could define on this, right? This type of random variable, sometimes it goes by different names. It could be like a categorical. Sometimes people call it dummy because it's either simple 0 or 1. Sometimes people call it an indicator, right? Because if it's not one of those, then it's 0. But if it is in that category, then it's a 1. And so this kind of a function, this kind of a random variable has a few different names, goes by a few different aliases. Okay, and then there are other, depending on your interest, depending on what your question is, you may find it helpful to define other random variables on this base set of events. Okay, and so here's another one, rolling one die again. If people don't say it's 6-sided, we assume it's a 6-sided die. The case number, or the ID number here, the event would be 1, 2, 3, 4, 5, 6. One random variable would be, well, how many dots are appearing? 1, 2, 3, 4, 5, 6. Another sort of indicator categorical one would be even. So we want to spot the even ones. Another might be we want to spot the ones that are divisible by 3. So 3 is divisible by 3, clearly 6, and then 1, 2, and then 4 and 5 are not divisible by 3. So that's another random variable, and there are other random variables that may be of interest. Yeah. Okay. So we looked at one coin, tossing one coin. So two. Then we looked at tossing 2 coins. So we looked at one die. Well, let's look at rolling a pair of dice. And so again, how many possibilities, right? So same thing. The first one, there's 6 possibilities. The second roll, there's another 6 possibilities. We multiply that out, and we have 36. So in fact, is a 6 by 6, and so this is the roll of the first one, the roll of the second one, the roll of the first one, second one, and so these are the simple events. So this would be the sample space. Say 6 cross 6 or something like that. Okay, so those are the events for rolling a pair of dice. Okay. And so simple, these are the individual simple events. Compound events, we might say one event, compound event is when they're both even. And so again, if they're both even, the first die could be 1, 2, 3, 4, 5, 6, but really only 2, 4, or 6 are even. So there's really only 3 possibilities to be even, and then they're both even. So the second one also has only 3 possibilities, right? So that's 9. And so you can see, in fact, there are 9. So we think we got all of them. We got all of them. Okay. Another compound event could be the sum is 7. So if you get a 6 and a 1, a 5 and a 2, 4 and a 3, 3 and a 4, 2 and a 5, 1 and a 6, those are where your 7s are. Another random variable could be the sum. So we add them up. So we take 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, 5 plus 1, 6 plus 1, and we get 2, 3, 4, 5, 6, 7, right? And then we just add them up. So this is a random variable, or one of many possible random variables on this sample space. Okay, so some compound events, some random variables, and just another view. So that's the sort of array view, 2 by 2 view. This is just a view of the same thing. This would be more like a tabular method, And so here we're assigning the case numbers. Here it's kind of it gives you a visual kind of 2D view of the sample space, and sometimes that's helpful. And so you might want to do that. In addition, you might also want to do the tabular view. There's this parable about the blind men in a village in India, right? And so the blind men are in the village, and everybody sort of talks about an elephant. They have no idea what an elephant is. And then one day they get the news, oh, there's an elephant near the village. Oh, let's all go out to see the elephant. So that somebody, guides them all out there, and they sort of interact with the elephant. And they come back to town and they say, wow, one of them says to the others, oh, wow, the elephant was so cool. It's like a snake. And then another one says to him, what are you talking about? The elephant is like a big wall, And then the third one says, you guys, what's wrong with you? The elephant was like a tree, right? And then another one says, how can you guys get it all messed up? The elephant is like a sharp spear, right? And so why is that, right? Because one of them, the sharp spear, was a tusk, right? Another one, snake, that one just touched the trunk, right? The wall was like maybe the body, and the leg was a tree. And so, the moral of the story is, the elephant, it is what it is. It's very complicated. Sometimes it's very helpful to have a particular view of the elephant or something complicated. And so, if you're dealing with something, this isn't so complicated, but it's a little bit complicated. And so sometimes it's helpful to have, this view. Sometimes it's helpful to have some other view. In accounting, if you've taken accounting, you may have heard of the income statement. You may have heard of the balance sheet. You may have heard of the statement of retained earnings. You may have heard of the cash flow statement. And you may wonder, why do we have these four things? It's like, well, the business is what it is, right? And so when we look at the income statement view, that sort of gives us one perspective. And then we shift around, and you've seen these maybe drawings of these complicated parts. There's like the front view, there's a side view, there's a top view, right? They give you all these different views. And so sometimes when you want to understand something complicated, it's important to look at it in more than one way. And then each way gives you slightly different perspective, slightly different insight. So here's just another way of the same thing, basically. Here, it's sort of long, but you can see there's, 36 of them. Of course, you already knew there's 36 of them. But now we're sort of assigning specific ID numbers, case ID numbers, or primary keys to particular outcomes. So it makes it a little bit easier to discuss them. Although, we could say the 2-4 event versus, event number 10, maybe the 2-4 event is easier, I don't know. And so the case when they're both even, you could put zeros and ones, but then that would make it a little bit cluttered, right? And so it might be easier to spot them if you just put checks in the ones that are relevant. And so you can see there's one set of 3, another set of 3, and the third set of 3, so 3 sets of 3 is 9. Okay, and so the compound 7, you kind of see, sometimes as you look through these things, you may see some patterns, right? And then, the sum of both die, just add them all up. And so you can see the pattern, 2 through 7, 3 through 8, 4 through 9, 5 through 10, 6 through 11, and 7 through 12. Okay, and so, listing out the compound event where they're both even would be some BE, both even, be something like that. Not break even, right? That's another model. This is both even in this case. And so, right, number 1, number 2, 3 would be 9. Okay, and so the sum 7 compound event would look like this, where you just enumerate them. Okay, so that was sort of the warm-up, and remember that we define probabilities on events, right? So once we have the events, then we assign probabilities. And so what are probabilities? Probabilities are fractions, right? And so if E is the outcome or the result or an event of a random experiment, then the probability of E is a probability that E is likely to occur, and it can be 0. 0 means that it's extremely unlikely. Doesn't quite mean that it's impossible, what did they say? They say that, you know, to think of, you know, 1 in a million. And so, you know, in China, where the population is, you know, 2 billion or something like that, 3 billion, if you're 1 in a million, you know, there's a few thousand people like you, right? So when we think, usually when you think 1 in a million, it seems like, oh, it's almost impossible, right? But if you have, you know, something that's 1 in a million and you have 3 billion people, well, there's a few thousand out there, right? So doesn't mean that it's impossible. It just means that it's extremely unlikely. And so probabilities can range from 0 all the way to 1, and any sort of numerical fraction in between. Okay, P is nearly certain to occur, right? And so, you know, how do we think about probabilities? One way to figure it out is to actually look at the data. So that basically that's what empirically means. And so this means, you know, afterwards, like obviously you have to have data to look at. And so, you know, like for life insurance or disability insurance, what's the probability? Or, you know, auto insurance, what are, you know, every day there's some number of accidents, and the accidents have some cost in the end, right? And so what's the likelihood of accidents and how much do accidents cost? I don't know. We would have to look at the data to gather that information. But as long as it's being collected, we could assess those probabilities and those costs later, after the fact. Classically, you know, sort of based on a knowledge of the components of the random experiment before you conduct the experiment a priori, right? So, I mean, could we determine the likelihood of an accident classically a priori? Not really. Like, we don't know what the likelihoods or probabilities are. It's kind of, you have to have the data. Subjectively, you could just say, based on my opinion, you know, we could say, well, you know, I think the chance of an accident is, I don't know, how many people do we have in Hawaii? A million, say 900,000, and I guess there's like 20 accidents a day. So is it 20 over 9 million? You know, so that will be sort of because I'm not actually looking at data. I'm trying to like guesstimate it based on my opinion, or I'm trying to make an educated guess, trying to make a judgment. And so it's like, well, since we don't have the data and we need a number, let's just kind of make one up, but, you know, try to make it in a logical way. And then at least we can get started and, you know, do some things, and then 6 months from now or a year from now, we'll collect the data that maybe we don't have it now. We'll collect the data, and then we'll look back, and a posteriori, we'll look back and see, did our judgment make sense? And then anyway, we'll have that data. So for the following year, we can actually do better in our estimation, in our predictions. Okay, so those are basically the three main ways that people actually assign a value to, or come up with a number that we say as a probability. So for example, if we were talking about a coin toss, I mean, just sort of classically, we'd say it's 50-50, right? Heads or tails. And, you know, in theory, the coin could land on its side edge and stay there. Maybe it, like in sand, you know, if it perfectly landed like a knife, then it wouldn't be neither heads nor tails, right? But we'll just rule that it's not going to land. It's going to flip. It's going to be heads or tails. It's not going to land, you know, I don't know, right? Standing up on its side, right? Classically, we'd say 50-50. Empirically, you know, we've got a bunch of people here. Maybe if we find 10 people, we get that each person gets 10 coins, flip 10 coins, and we pool all the results. And so then we look at it, and so then we would say number of heads divided by the number of total, that would be the probability. So that would be by conducting an experiment, by looking at the data, by getting the data. And subjectively, well, I think there's two possible outcomes. I think it's a fair coin, so it would be based on that, right? What is the probability of exactly one head? You know, and so it may not be possible because you would just do it the classical way, right? So these are just some examples of us trying to get a number, a fraction probability, either the empirical way, the classical way from analysis, or, you know, if it's more complicated, you just kind of have an opinion on what it might be. Okay. And so in probabilities, sometimes you hear about the law of large numbers. And so when you compute empirical probabilities, so it's these empirical probabilities, the more times you run the random experiment, the closer you will come to estimating the true theoretical probabilities. And so there's more sections, more on this in the book. Okay, so now we want to come to look at some more examples. And we want to start looking at combinations of events. So for example, if we think about rolling a die, and so the possible outcomes are, you know, the basic elementary events, simple events are, you know, there's a 1, 2, 3, 4, 5, or 6, right? On the other hand, we could have one event, say E for the evens, you know, so evens would be 2, 4, 6. And then, say, event F could be 4 and above, 4, 5, or 6. Okay? So, if we assign the, you know, or assign the cases or look at the cases like this, event E would have, when there's a 2, when there's a 4, when there's a 6, there's 3 possibilities. And event F, 4 and above, would be also event when the simple event is 4, 5, or 6. And so again, there's also 3 of them. And we want to ask questions like E or F, you know, what's the probability of E? You know, what's the probability of F? What's the probability of E or F? You know, either one, E or F. Or what's the probability, another question we might ask is what's the probability of E and F, where they happen at the same time. Okay, and so we have this sort of this U-looking symbol here that's for union. Maybe you've seen that before. And the union is associated with OR. The intersection is associated with AND. So sometimes you'll read a problem and they'll say, you know, the probability of E is this, or A is this, the probability of B is this. What's the probability of A or B? And you shouldn't say, well, I don't know. You should say, oh, they're asking about OR, that's union. Okay? Or sometimes they'll say, you know, what's the probability of E and F? And you shouldn't say, oh, I don't know, right? You say, oh, I have to use the intersection. What's in the intersection? And that's where I find the probability. Okay? Also, there's a concept of what's called the complement. And so if, you know, this is our sample space, and if this is set E, you know, what's sort of the opposite of E, or what's not in E, E bar. Sometimes some books will do E prime or E asterisk with the little asterisk there. And that's the complement. And so it's the elements in the set, the events in the set that are not in the main set. Okay, and so if F is 4, 5, 6, not F would be 1, 2, 3, or the complement of F, or F bar would be 1, 2, 3. Okay, and so, you know, if here it's kind of easy to see E or F or the union, right? Because it's in E, so it's in both of them. Here, the 4 is in both, so it's there. 5 is in F, so it's in their union. And then 6 is in both of them, so clearly it's there. And so by having the table, you can easily see E or F. Right? And so 1 is not in E and it's not in F, so it's not in E or F. 3 is not in E, it's not in F, so it's not in E or F. Right? But basically, if it's in either E, it's in their or if it's in both, clearly it's in their or, in their union. Okay. And F, it would have to be in both. And so here, when you have it in this column table view, it's easy to see, oh yeah, this one, no, because it's in E, but not in F. So it's not in their intersection, right? Here, it's in both, so yep, that's in their AND, that's in their intersection. 5, it's in F, but it's not in E, so no, it's not in their AND, not in their intersection. And yes, here it is, it's in both, so there, it belongs in there. So there's only 2 overlap, in a way. Okay. So sometimes people have come up with these Venn diagrams, not a big deal. The sort of the big square is the universe, or the superset, the sample space. Okay, sort of borrowing some ideas from set theory, but we're sets, superset, the union, I think. But in probability, we deal with sample spaces and events, and event is basically a set, right? It can be a simple set or a compound set, right? And so anyway, we draw the circle, oval kind of a thing for E, draw another one for F, and then the part where they intersect, that's the intersection, and their union is everything that's in both, right? And then there may be some items that are outside of those. Okay, so applied to the role of the die, right? E is 2, 4, 6, and F is 4, 5, and 6, right? And so how do you know this? Well, it actually helps to have this done, right? Because otherwise, you have this circle for E, and then you have to put the 2, 4, 6 in there, but does the 4 and the 6 go outside or inside? So you kind of have to scratch your head. So in order to put one of these together, it actually helps if you have the table done first, because then you could say, okay, in the intersection there's 4 and 6. Okay, so here's the intersection, so that's where I put the 4 and 6. Okay, so then here 2 is in E, but it's not in F, right? So here E is a 2, but it's not in F. That's kind of what this is saying. It's in E, and it's not in F, right? So this is E, actually. E you can think of as the union, putting together what's in E but not in F, and what's in E and in F, right? So this is kind of very, very systematically saying E is composed of the part, there's some, if there are any elements that are in E and not in F, they go over here, and they're in E and F, they go in the intersection. And similarly for F, what goes here are the ones that are in the intersection, right? 4, 5, 6, so this is their intersection. And then F would be the union of what's in both E and F, and what is over here in F, but not in E, or and not in E. Okay, not E. So that would be 5, right? So here clearly 5 is in F, right? But it's not in E. So it kind of goes over there. And then clearly, if we're looking, so this is the union, right? 2, 4, 5, 6, right? 2, 4, 5, 6. This union column, that's what's inside this kind of 8, sideways 8 or infinity symbol. So you kind of ignore but just look at the outer boundary. It's like sideways 8 or infinity symbol. So that's the union. And then what's not in there. 1 is not in there, and 3 is not in there. And so they are actually in the sample space, right? But they're not in E, and they're not in F. Okay, so that's kind of where you keep track of everything. Okay. So how do you assign, probabilities? Here, we assume that they're all equal, right? So it's equally it's a fair die. We assume it's a fair die, and that the die is not weighted at some sometimes you see these translucent die, so you can see through it. On a solid die, you don't really know if somebody is drilled in and they put some lead on one side to make that the heavier side, to make the opposite face more likely to occur. So assume we don't do that. Assume we have a fair die, then everything is easier. Right, and so to find the probability, you just take the number of events that are in E times the number of events in the sample space, the number in the total, and that's your probability. So what's the probability of E? where E is the evens on a six-sided die. Right, so we just sort of apply this formula, right? The probability of E, which is actually the probability of, say, 2, 4, and 6, right? So that's equal to the number of evens over the number of the sample space, right? And so we could really see, oh, this is 3 and this is 6, right? But you could also say, you know, what's the number of in 2, 4, and 6? And then what's the number in, you know, the number in 1, 2, 3, 4, 5, 6. Oh, oops, wrong way. Close off the set and then close off the function. Okay? However you want to think about it, right? And then the probability of F, right, is equal to the number in F, right, and the number in the sample space. Okay, and so actually they're the same size, right? So E and F both have 3 elements, sample space has 6, and so we might simplify this to be a half, right? So we could also simplify that one to be a half. Okay, and so the probability of E intersect F, right? So that's the number in E and F over the number in space. So what's the intersection? That's the number that's in the intersection is 4 and 6. So 4 and 6 is only 2 of them out of 6, and so we can simplify that to 1/3. Right, so we're really just applying this formula. But in the first case it's the set E, second case it's the set F, and in the third case the set is the intersection set. Okay, so what about the union? E union F, probability of E or F, right? Again, that's the number in E union F, E or F, over the number of in the sample space. Okay, and so what do we have there, right? We have the sample space is really 2, 4, 5, 6, right? 2, 4, 5, 6. So we got a 2, 4, 5, 6, basically everything but 1 and 3, right? Over number S6. And so that will be 4 over 6, which we can simplify to 2/3. So this is no, right? Probability of E union F is not probability of E plus the probability of F. Right? If you take, because this, right, the probability of E would be 1/2, and the probability of F is 1/2, and so that's equal to 1, and that's clearly not equal to 2/3. Right? And so if we take the probability of E, right, that's sort of this whole thing, right? So this whole thing is a half, probability of a half, right? And then the probability of F is this whole thing is also the probability of F, 1/2, right? And so that's why if we take a half plus a half, we get 1, which is not the probability of their union. But if we take the probability of E, we kind of have all of this probability, right? And we take the probability of f, we kind of have all of this. And so what's the source of the excess, right? The source is the fact that we've included, or that we've got the probability of the intersection twice, right? Does that make sense? When we do the probability of E, we do all of this probability, right? And we do the probability of F, we do all of this probability. But then that includes this intersection twice, right? Because once we've picked it up with E, and once we've picked it up with F. So can we correct this formula? P E union F equals P E plus P F. How can we correct it? How can we get it so that actually it works? Right? Can anybody see how we can fix it, the formula, so that it would work? If we do E, we're getting all of this, including the intersection. And then we add the probability of F. We again do the whole thing, which includes this intersection. So by doing probability of E and probability of F, this includes their intersection, the intersection of E and F. This also includes the intersection of E and F. And so that's why when we add them up, we get too much. So if we have too much to get it right, what should we do? We should take away. How much should we take away? Take away the intersection, right? So if we minus probability of E intersect F. Yeah, and oh, by the way, every now and then you'll find a book where they just write EF. So I might accidentally do that. So I'll try to remember to do E intersect F. But the shorthand is that if you do EF together without any symbol, it's AND. It's intersect. Okay. So this would be 1/2 plus 1/2 minus 1/3, right? Because this is the intersect, right? Minus 1/3. So we bring this minus 1/3 over there, and then it's 2/3, and so that's the right answer. Does that make sense? So actually, this is given a name. Right? This is given a name. What it is? This is the general law of addition. Okay? So if you know the probability of F, if you know the probability of E, if you know the probability of E, and you have to know the probability of their intersection, you can find the probability of their union. You take the probability of the first set, probability of the second set, and remember kind of this picture. You got E and you got F, and so this intersection you're double counting. You got it when you added E, you got it once. When you add F, you got it twice, the intersection. And so because it's in there twice, you have to subtract it out once. And then when you do that, you can actually compute the union. Okay? Okay? So let's sort of continue this example, but now with dice, and E is same evens. But now we're going to consider a slightly different set, which is called the non-even prime. So instead of calling P, which is like probability, we'll go to the second letter, which is R, so the non-even prime. So E, so 2 is a prime number. So 1 is not a prime number, 2 is a prime number, it's the only even prime number, and all the other prime numbers are odd, and so the non-even primes we'll just call R. So in this case, it's only 3 and 5. Only 3 and 5, right? And so now the union is bigger than the other one. They have no intersection, which is why we wanted to look at this case, because now there's no intersection. And not E, not F are out there. And so you can see if we do the, so, having this knowledge ahead of time makes drawing, it's like, the picture is supposed to make it easier to see, but if you actually write out the table, then it's easier to draw the picture. Kind of weird, but anyway. So here, you can see that E is 2, 4, 6. Before, right, we still had E being 2, 4, 6, right? But there was some intersection, right? Now that the intersection is empty, the set E is over there, and the set R is over there, right? And actually, there's a name for this, and it's called mutually exclusive. And so this means that the intersection, so E and R intersection equals a null set. So if it's no elements are between, no events are shared, then it's called mutually exclusive, right? And so if we have the probability of E, right, clearly the probability of E, right, is from before. We kind of did that last time, and so we don't have to do it all over again. Probability of R, right, you can kind of see how it's 2 over 6, which is equal to 1/3, but formally, right, it will be equal to the number in R over the number in S6, right? So the number in R is 2, the number that is 6, and so that's equal to 1/3. Okay. So probability of the intersection, E, R, probability of E intersect R. So here I did that, a little bit of a shorthand where sometimes people leave out the intersect. Okay. So the number in E intersect R over the number in the sample space. So there's nothing in the intersection, so the probability of the intersection of E and R is 0, empty, right? Because it's the empty set. Okay. Oh, sorry, this should be R over there. So what's the probability of E union R, right? Actually, we know it's 5 over 6, right? But we can actually do the probability of E plus the probability of R, right? Which is equal to the probability of E is 1/2, and the probability of R is 1/3, right? So 1/2 oh sorry, no, it's 2/3. Wait, what? It was 1/3, yeah. Okay. Oh yeah. So we do 3/6 plus 2/6 equals 5/6. Right. So 1/2. If we want to add 1/2 and 1/3, we have to convert to sixths. So 1/2 is 3/6, 1/3 is 2/6, and then 3/6 plus 2/6 is 5/6. Right, and so notice that we can just go ahead and add the probability of E plus the probability of R. How come we don't have to subtract the probability of E intersect R. Like we did, remember the general law, we sort of in the previous page, we did this whole thing about, you know, look, when you add this, you're picking up the intersection. When you add this, you're picking up the intersection. You actually have to, you got the intersection in there twice. So make sure that if you add the probabilities, you take it out and then it works. Here, it's a little bit different, right? Because the probability of the intersection is 0. So this is actually equal to 0. And so we don't need to factor it in, right? And so, does that make sense? So this gives the special law of addition, which applies only when what? Mutually exclusive. Okay, so if you know that the two sets are mutually exclusive when mutually exclusive. So that's kind of this case, right? So the special law of addition is kind of when mutually exclusive. Okay, does that make sense? Okay, so I think that's about it, right? Brings us to the end. We looked at events, outcomes, observables, what's observed. Events can be simple or compound. We looked at some examples. The collection of all the events is a sample space. In statistics, it's called the population. So the total thing. There is an empty set. It's useful to think about. Null set also. Random variable is a way to assign numbers. Okay? And so we'll be coming to that soon. Probabilities basically are fractions. And we looked at OR, which is a union. So if you read problems and you see OR, you want to think about union and the general law of addition, right? Or the special law of addition if they're mutually exclusive, right? So if you see these two sets, you got to figure out, are they mutually exclusive or not? Because it depends how I handle them. Okay, remember and is intersect. Okay, and the general law of addition and the special law, if they're mutually exclusive, right, which means the intersection is the null set or empty set, we have the special law of addition, right? And then don't forget TVM stuff. We'll have an exercise on that later. Okay, so see you tomorrow.